Hello, SWIC Earth Science students. Welcome to another recorded lecture. This week in week 7, we will be studying minerals, rocks, and the rock cycle. So this is covering 2 chapters. Those chapters are Chapter 2 and Chapter 3, Matter and Minerals, and Rocks, Materials of the Solid Earth. Again, make sure you read the book. I will cover things in a slightly different way. Be forewarned, this is going to be a long one. We are covering 2 chapters. There's a lot of stuff in here. We are not going to cover everything in lecture that's in the textbook, so make sure you read the textbook. So first we are going to start with minerals. So we're going to look at what makes up minerals, what is a mineral, and how do we identify them. And we will be looking at minerals in lab this week. So we have to start small. So atoms, elements, and minerals. So subatomic particles, there are 3. We have neutrons, protons, and electrons. These make up our atoms, which are the elements. The atoms combine together to make compounds. Those can be minerals or they can be organics. Minerals will combine together to make rocks. Organics combine together to make living things. And those rocks make up our Earth. So we are looking at this side of the system. So these subatomic particles, there are 3 of them. They each have their own job. So we have different charges and weights for our subatomic particles. The weights will be given in AMUs, atomic mass units. The charge will be either positive, negative, or neutral. The atomic number is going to be the number of protons that an element has. The atomic number is what defines the element. Every element has a unique number of protons. If you change the protons, you change the element. The atomic weight is how much the element weighs, and that ends up being, we will see the number of protons, which have an AMU of 1, plus the number of neutrons, which also have an AMU of 1. So the number of neutrons can vary, and that will change the weight of the element. This is what we call an isotope, where we have a different number of neutrons, so we're changing the weight. Electrons will be not important for weight. They will be important for bonding because of the charge. So if we look at our particles, protons have a positive charge. So if we have extra protons, we're going to have a positive charge on our atom. Electrons have a negative charge. If we have extra electrons, we will have a negative charge on our atom, and neutrons are neutral. So it doesn't matter how many neutrons we have, that doesn't change our charge. So neutrons are important for the mass and isotopes. Electrons are important for the charge, which will be ions. So the element is going to be defined by the atomic number. That is the number of protons. Carbon always has 6 protons. If you add 2 protons, that carbon's no longer carbon and is now oxygen, because oxygen always has 8 protons. The mass number is or the atomic weight is the number of neutrons plus protons, and that can change as you vary the number of neutrons. These are isotopes. So isotopes are important for things like radioactivity. And then the charge can also change as the number of electrons changes. So again, the number of protons is always going to be defining the element. The number of electrons will normally start off matching the number of protons because we start off balanced. But elements are always trying to get full electron shells. An electron shell is full if it has 8 electrons. So we're trying to get to that point. Or lose electrons to get to, empty a shell. And so as you change those number of electrons, if you take on extra electrons, you will get a negative charge. If you lose electrons, you will end up having more protons, so you'll have a positive charge. And again, these are ions. So here we have a periodic table. This gives us the information about our elements. So the symbol is going to be an abbreviation. So H is for hydrogen. Below that we will have the atomic mass, which again is neutrons plus protons. At the top we have the atomic number, which is the number of protons. And where it sits is going to basically tell you your electrons. So hydrogen has no electrons. It also has no neutrons. Helium has 2 protons and 2 neutrons, so it has a mass of 4. Remember, with hydrogen, these are the 2 building blocks. This blue column over here are the noble gases. They are places where we have a full electron shell. So all of the elements want to get to this state. They want to have these full shells. So elements that are one short, such as like fluorine, chlorine, etc., they like to gain an electron to fill their outer shell. Elements that have one extra, like lithium, sodium, potassium, etc., like to lose an electron to have a full outer shell. So these over here tend to be +1, these tend to be +2, these over here tend to be -1, -2, and so on. And so we will see that charges that are the same value but opposite sign like to meet to come together because they can basically fill each other's shells. So there are different ways to bring elements together. This is called bonding. So bonding will form compounds, and the types of bonds will impact the compound structure. So some bonds are stronger than others, some are very weak, and that's going to impact the properties of the material. So atoms are going to be most stable when their outermost shell is full. So they can either lose or gain an electron in order to make that outermost shell be full. These are called ions. So they have a charge, and the number of protons is not equal to the number of electrons. So if you have a net positive charge, it's called a cation. If we have a net negative charge, it's called an anion, and opposite charges attract. So sodium has a +1 charge. Chlorine has a -1 charge. Sodium and chlorine like to come, or chloride rather, like to come together. That's sodium chloride, which is table salt. So we see that these charges will attract each other. So again, there are different ways we can bond. We have what are called ionic bonds, which is what I just described. So this is where one element or one ion will give up its extra electron to an element or an ion that needs an electron. So the positive, the cation, gives up an electron to the anion so that both of them will have a complete shell. We can have a similar type of bond that is stronger called covalent bonds. So covalent bond is where instead of actually giving up the electron, in this case both ions need the electron, and so they share the electron. And so that we have an example of this here. These ones circled in red are being shared between 2 different atoms, and both are using that electron, and so it bonds them quite closely together. So again, ionic bonding is where we have electrostatic attraction between oppositely charged ions. These have either lost electrons, so those are the cations, or gained electrons, which are the anions. And again, this is how this happens. We're actually exchanging an electron. Covalent bonds is where we're sharing electrons in order to acquire a stable arrangement. An example of this that's very common in nature is silicon and oxygen. So the silicon tetrahedron. So we have, so an example of that silicon tetrahedron is this here, where we have, sorry about that, we have 1 silicon and 4 oxygen surrounding that silicon, and so they are going to be sharing electrons because both of the ions need those electrons. The silicon has a charge of +4, and the oxygen ions each have a charge of -4. There's actually a net charge on the tetrahedron, which allows it to bond to other things, but in this case the silicon and the oxygen are actually going to be sharing electrons to make them both more stable. So that's an example of covalent bonding. There are other chemical bonds that aren't as common, or well, they're common, but we don't talk about them as much. So we have metallic bonding. That's what's in this image. So this is where we have a electrostatic attractive force between electrons and positive charged metal ions. It's basically sharing free electrons among the structure of positively charged ions. So this is what makes metal very malleable, because this is free sharing of electrons. We can have hydrogen bonds. There is a primarily electrostatic force of attraction between a hydrogen atom, which is covalently bound to more electronegative atom or group, particularly the second row elements nitrogen, oxygen, or fluorine. The hydrogen bond donor and another electronegative atom bearing a lone pair of electrons, and then the hydrogen bond acceptor. So basically we have this, you have the donor would be the negative atoms, and the receptor would be the hydrogen atoms. And then we can have van der Waals interaction. So this is a special case where we have, again, electrostatic attraction, but we have attraction and repulsion between atoms, molecules, and surfaces. They're different from covalent and ionic bonding in that they are caused by correlations in the fluctuating polarizations of nearby particles. This is due to quantum dynamics. So they are a very weak type of bond, which may be apparent in the fact that we're looking at things like talc and graphite, which are very, very soft materials. So if we want to think about the strength of bonds, covalent are going to be our strongest bonds, where they're sharing those electrons. Hydrogen bonds will be fairly strong as well, because that's a type of covalent. Ionic bonds are not quite as strong as covalent bonds. Again, the metallic and the hydrogen bonds are not, or they're special types of bonds, so their strength is a little bit hard to correlate across. And then van der Waals bonds are going to be the weakest. So now let's talk about minerals, the compounds, when we take those atoms and combine them into something. So this is slightly old. It's still true. There are more than 4,000 known minerals. It's higher now. There are 50 to 100 new minerals discovered annually. So here we have an old screenshot of a mineral discovered in Australia. We are finding new minerals all the time that typically are only found in one or two locations. They're not extremely common. We also theorize minerals at times. So we know that a certain structure should exist with a specific chemistry at certain conditions. The reason we study minerals is because minerals are going to make up rocks, and what minerals are in the rocks are going to determine the rock's behavior, and that's going to be important for us to understand the Earth. So what is a mineral? A mineral has a very specialized definition in geology. So they are naturally occurring, mostly inorganic crystalline solids formed by geologic processes and with a definite chemical composition. So this is an example of malachite. It's a type of copper ore. It contains copper plus some other chemicals. So here's the definition. We are going to go through this definition and break up what all these different things mean. So it has to be a mineral. We have to meet all these criteria. You can't just meet some of them. It has to meet all of these criteria. So I am going to go through all 5 of these. So naturally occurring. A mineral is created by natural processes. So humans can recreate natural processes to make minerals, and those are called synthetic minerals. So you see this in the jewelry industry. Synthetic gemstones are not real minerals. They are created in a lab, or lab-created gemstones. So if a crystalline compound has never been found in nature, it can't be recognized as a mineral. We can theorize that it should exist, but if we haven't found an example, we can't name it as a mineral. So, for example, in the lab, mineralogists have reproduced a magnesium silicate that's thought to occur naturally in the mantle between 670 kilometers and 2,700 kilometers. They gave it a name, magnesium perovskite, but they couldn't give it an actual mineral name because we hadn't found an example of it, a naturally occurring example. So it's still hypothesized. It has to be solid at room temperature. So remember, we can have solid, liquid, gas, or plasma. So at room temperature, at Earth's surface temperature, it needs to be solid. So native mercury is not solid at surface temperature, therefore it's not a mineral. So yeah. Abiogenic. So it can't only be the product of living organisms. So for example, calcium carbonate can be the product of marine life. It's found in marine shells a lot. It's also found in nature, so it's able to be a mineral, even though it can also be produced by organic processes. Whereas your tooth, for example, is not being found in, that's probably not the best example. Wood, for example. Wood is organic. It's not found in non-organic situations, therefore it's not a mineral. They have to have a definite chemical composition. So they can be very simple, calcite, calcium carbonate, calcium, carbon, and 3 oxygen. Quartz is silicon and 2 oxygen. Ice is H2O, that's the same as water. Ice is an interesting material because technically ice can be considered a mineral, maybe, but it typically isn't. They can also be extremely complex. So at the bottom here we have 2 very complex, messy mineral chemical structures. So we see that we have, for example, these things in parentheses. So the things in the parentheses, we do this if, for example, there is a compound that is part of the mineral structure. We will put that in parentheses because sometimes you will have multiples of that. For example, this OH, that is a type of water, and we have 2 of those. So it's not true H2O, but it is representing water being in this structure. Sometimes we have these parentheses because we can have substitutions. So for example, in this biotite, we have Mg, Fe, and there are 3 of those. That means that in this spot we can have magnesium, iron, or a combination of it. We just need 3 of that material in that spot. We can also have other substitutions in for things that fit in these spots as well, and that makes variations in these minerals. So hornblende is one of the messiest chemical structures of the minerals. Basically, it's kind of the kitchen sink of minerals. It takes almost anything go in. It has to have a crystalline structure. So a crystalline structure means that the atoms inside are organized in a predictable manner. So if it does not have a ordered predictable matter for the atoms, it's called glass. And for example, obsidian is a glass, which would not be considered a mineral. It's not actually it's not actually quartz, even though it's the same composition. We have to have a predictable order for the crystalline structure for the atoms. Some of them are very, very complex, some of them are much simpler, but it has to be predictable. So this means that we will have crystals. A crystal is a single continuous piece of crystalline solid that's bounded by flat crystal surfaces. So this image is showing the Washington Monument when it was being worked upon, and they had latticing or scaffolding all around it. You can think about these as this structure that holds the atoms together. And we would have an atom at each intersection, and this makes it a very predictable, repeatable object. So this is what we mean by crystalline structure. Again, some of them are very complex, some of them aren't very complex. And we will see that there's a difference between this property, the crystalline structure, and then other properties later on. So minerals, because they have a definite chemical composition and that internal crystalline structure, they will have any sample of the same mineral will have the same properties. So all specimens of a given mineral have the same physical and chemical properties. This is going to be determined by the way the atoms are packed together into that crystalline structure. So these physical properties are going to depend on what atoms are present, how they are arranged, and how they are bonding to one another. And this is how we're going to identify minerals. This is how we're going to say what different things are. So there are many physical properties that specimens should share. We will not use every single property for every single sample. Some of these can have variety in them, for example, color, which is why we don't tend to rely on that type of a property for all minerals. So we're going to look through all of these as well. So crystal habit. So this is that crystalline structure. So it's the arrangement of faces reflects, the arrangement of the crystal faces will reflect the internal atomic structure. If a crystal, this is defined as if a crystal is allowed to form in an unrestricted environment, it will develop these natural faces and assume a specific geometric form. So this image is from, these are actually a variety of gypsum, which is actually a fairly soft mineral, but they grew unrestricted in this cave. I believe it's down in Mexico. And so these are huge. There's a person standing here. So this is what can happen if we grow in an unrestricted environment. And we can have different shapes. We can have diamond shapes. We can have cubes. We can have prisms. We can have blades. We can have like dodecahedrons. And the shapes will sometimes be very diagnostic for a mineral, but not always. And again, this, I want to emphasize, crystal habit is how the crystal grows, given the chance to grow. We're going to see later on there's another property that is similar, but happens in a different way. So here's some examples of habit. So we can have a cube, so pyrite, fool's gold. We can have blades. Kyanite is one of my favorite minerals. Grows in the blades, is the blue part. We can also have fibrous habits. So this is chrysotile. This fibrous habit is actually a specific type of habit that's what makes asbestos. So this happens mostly in amphiboles, and it's very fine needles that break off and can be inhaled and then be problematic to people's lungs, and asbestos is a big issue. So the next property is similar to habit and often confused with habit, but it's different. So cleavage and fracture is how a mineral breaks, and it will break along planes of weak bonds. So we can have up to 6 planes of cleavage. The number and direction in a given mineral species are going to be characteristic for the mineral. Fracture happens when all the bonds are equal in strength, and so there's not a preferred direction of breaking, and so the rock basically will, the mineral will shatter instead of breaking in a predictable way. So cleavage is where we are breaking the rock, and it will break along the weak parts of the lattice. So it is related to the atomic structure as well, but this is how it breaks, whereas the crystal face is how it grows, which again is related to the atomic crystalline structure. So cleavage can be distinguished from crystal faces because it is through going. The faces are only going to be on the external of the crystal. So when we look at this image, we can see that there are breaks that go all the way through here, whereas these planes are only on the surface. So we can have cleavage in one direction, that would be like a sheet. We can have cleavage in 2 directions at 90, where we basically will be chopping it. We can chop it this way and this way. We can have 2 directions not at 90, so same idea, only it's not squared. We can have 3 directions at 90, so that's where we're going to break it into actual cubes. And we can have 3 directions not at 90, which is where we're going to break it into rhombs. Whereas fracture is, we call it conchoidal fracture when we can see these pressure rings, or irregular fracture when we don't. This is where if we break the material, it's not going to break in a predictable pattern. This happens because there is all of the bonds are equally strong, so there's no preferred bonds to break. So the next property is density, which if you remember from week 1 is also called specific gravity. So this is the weight over the weight of an equal volume of water. It's the heft, so how heavy it feels. Galena, which is a lead mineral, is very hefty, whereas quartz is not nearly as hefty. So, if you had the same size samples in either hand, the galena would feel much heavier, or be much heavier rather. So, specific gravity can be very helpful for certain minerals such as galena that have an unusually high specific gravity. It's not as helpful for all. Many minerals have a similar specific gravity, so it's typically not the most useful for identifying. Hardness is the next physical property. So this is can be defined as the scratching resistance of a mineral, or how hard it is. This is due to the strength of the atomic bonds. So to measure the hardness of minerals, we use a thing called Mohs hardness scale, which is 10 minerals of known hardness: talc, gypsum, calcite, fluorite, apatite, orthoclase, quartz, topaz, corundum, diamond. The way I was taught it is the girls can flirt and other queer things can do. Some people say the geese can fly and open quaint tea carts downtown. You can come up with your own silly sentence for this. Talc is very, very soft. So talc is what they make baby powder out of. It's really soft. Gypsum is what they make drywall out of, gypsum board. Your fingernail is a 2.5, which means that either of those you can scratch yourself. It's a little bit unnerving for some people to scratch the minerals. A copper penny is about 3.5, so it is between calcite and fluorite. Glass and steel are about 5.5. That is between apatite and orthoclase. A steel file is about 6.5. That's between orthoclase and quartz. As we keep going up, we're going to keep getting harder and harder. Diamond is the hardest naturally occurring substance. All of these top 4 are gem minerals. So quartz in many colors makes different gemstones. So amethyst, citrine, there's some other ones. Those are all quartz. Rose quartz, smoky quartz. Topaz comes in many different colors. It tends to be kind of there are a lot of yellowy topazes. I think topaz is typically always called topaz when it's a gem. Corundum is either, if it's red, it's called a ruby. If it's any other color, it's called a sapphire. I always find that one fun because my birth month is July, which means that my birthstone is a ruby. My mother and my sister were both born in September, so their birthstone is a sapphire. They are the same mineral, corundum, except the ruby's worth more. And then obviously diamond. These are all very hard minerals, so they can be cut to be pretty, which is why they become gemstones. Next mineral property is luster. So this is the way a mineral surface scatters light. So we can divide it into metallic, which means it looks like metal, such as this pyrite up here, or non-metallic. And non-metallic, there are a bunch of sub-definitions. Honestly, most of the non-metallic, they look very similar. So whether or not something is satiny or silky, it looks very similar. The only one that really, looks different from the rest of these would be earthy, so where they're dull. So most people make the distinction of metallic or non-metallic and then don't go much further with luster. But metallic luster is rather diagnostic because you suddenly cut down your option of minerals quite a bit because only a few minerals have a metallic luster. So here's, again, this is how the mineral surface scatters light. So we have metallic and non-metallic. Color. Color varieties will often reflect trace impurities. So these are things that get stuck in the mineral structure but don't change it enough to change it from being that mineral. It's diagnostic for some minerals, not many, but some. For example, olivine is always green. But there are many, many minerals that can also be green. And there are some minerals that come in a variety of flavors or colors. So for example, quartz comes in almost every color under the rainbow. So Color is one you have to be very careful about when you're using it. Don't rely on color. Every student who's gone through a specific mineralogy course has been tested in a lab test where they are handed either 5 black minerals or 5 white minerals, and they have to identify which one's which. Every single lab instructor does this. A more diagnostic property than color is streak. So streak is the color of a powder produced by crushing the mineral. This tends to be more consistent for minerals. So what we do is we scrape our mineral on unglazed porcelain. It's called a streak plate. The streak color, again, is going to be less variable than the crystal color. What we see in this image is someone streaking a mineral called hematite. Hematite can come in a variety of colors. Sometimes it's reddish, sometimes it's more grayish, but its streak is almost always reddish brown, unless it's been altered enough that it's starting to become a different mineral. So there are times when a mineral will not produce a streak, that we're scratching it on our streak plate and it's not producing a streak. So why may it not do that? If the mineral is harder than the streak plate, so say you're trying to streak something like topaz, it will not powder against that plate because it is harder. You will actually end up scratching a line in the streak plate. So if you don't observe a streak, it's either that your mineral is too hard and you can't crush it on the plate, or it's that you're using a white plate and your mineral has a white streak. We do have, I think, one black streak plate. We have more on order, but if you think that you should be getting a streak and you can't observe one, it may be that your streak is the same color as the streak plate. There are also special physical properties. So these are things that are somewhat unique to one or two minerals, and they tend to be very diagnostic. So effervescence. This means it reacts to acid, it fizzes. So calcite will fizz if you drop very weak acid on it. That's what we're seeing here. This is the same reaction that happens in nature with acid rain. And so this is why marble headstones are very hard to read after not very many years, because they have a lot of calcite in them, and so it's being eaten away by the acid rain. Magnetism. So magnetic attraction, either it attracts a metal or it reacts to a magnet. So there's a mineral called magnetite that surprisingly is magnetic. Other minerals can be magnetic as well. Taste. Halite, rock salt, tastes like salt because it is salt. It's just salt. Taste is one. Be careful. Many geologists will lick and bite rocks. I do not recommend doing this in a classroom setting, because who knows if someone has, say, maybe tried to fizz that halite, and there may be acid on it. So in this class, please do not lick the rocks. Just believe me that we do this sometimes in the right environment. Smell, again, similar to taste. It's going to be only for a few. Sphalerite is a sulfur mineral. It smells like sulfur, so it smells like rotten eggs. Feel, so a tactile response to it. So talc feels like baby powder. It's very soft and silky. Graphite has a similar feeling as well, but graphite has a very different color. Graphite has the property that you can write with it very easily because it's the same stuff that's in your mechanical pencils. So that would be an example of a special physical property. So basically we will use those different physical properties. We will categorize the physical properties of a sample, and then when we have enough of them, we will go through and see what mineral fits those properties, and that's how we identify minerals. So when we talk about the names of minerals, minerals will be separated by their principal anion, so the negative ion, or anionic group, so the negative molecule. So the mineral structures are going to depend on the sizes of these ions. So only about 50 minerals are abundant, and the silicate group is going to be the most prominent of those. So silicate is where you have the silicate anion group. So that is that silicon tetrahedron where you have one silicon with 4 oxygen around it. We'll talk about them last. So, first one we're going to talk about are oxides. Oxides are where you have an O2 negative. So these will bond with metal cations. So iron, different flavors of iron, titanium, they will bond to this oxygen. So magnetite is an example. Hematite, rutile. Magnetite and hematite, they look very similar. They are very, very similar. Hematite can actually turn into magnetite as it takes in more oxygen from the environment. It can actually change into magnetite. You can actually have magnetite going the other way too. We can have sulfides. So this is a metal cation bonded to a sulfide anion. So you have one sulfide and it's one negative charge. So pyrite, which is iron, galena, which is lead, sphalerite, which is zinc. So these tend to have metallic lusters. We can have sulfates. So sulfate is where we're bonding to the sulfate anion group. So this is 1 sulfur and 4 oxygen and has a net charge of 2 negative. So that's what the 2 negative up here means. So these tend to form by evaporation of seawater. So examples would be gypsum, which is a very soft rock, and anhydrite, which is also very soft. So gypsum has a bit of water in it, anhydrite does not. It's been dehydrated. Both of these will have fairly weak bonds, which is why they're so soft. Halides. So this is where we have either the chloride or fluoride anion. So fluorite would be an example where it's calcium and fluoride. Halite is sodium and chloride. These tend to bond pretty strongly. They bond with ionic bonds. Carbonates. So this is where we have the carbonate anion group. So we have carbon and oxygen, and it has a net 2 negative charge. These form from precipitation. So this is going to be coming out of a fluid, whereas the evaporation is where the fluid dries out. This is where it's actually coming out of the fluid. So examples of this would be calcite, which is calcium, carbon, and oxygen, or dolomite, which is similar to calcium, only now we have some magnesium in there. So these have, similar shapes. The way you tell the difference between calcite and dolomite is that calcite will immediately react to acid. Dolomite, you have to crush it up before it reacts to acid, and it's because of this combination of magnesium in there as well. We can also have native elements. So a native element is where it's just that element, and then it's solid at surface temperature. So these tend to be metals. So Cu is copper. I'm looking around. My copper dog is not in here with me. Au is gold. Ag is silver. These tend to form with each other, and they will form these, veins basically coming out. And then the final group we're going to talk about are silicates. So silicates are called the rock-forming minerals. So this is where you have 1 silicon and 4 oxygen, and you have a net 4 negative charge. So they constitute almost the entire crust and mantle of the Earth. They are the most common minerals. An example will be quartz. Quartz is a bit of a unique example because it is just silicon and oxygen. So you have enough of these silicate tetrahedrons to balance each other out. So 98% of crustal mineral mass is from 8 elements. These are our 8 elements. I already talked about this. The mantle tends to be, again, the oxygen and the silicon with some iron and magnesium. The crust has the rest of it. So all these have the silicon-oxygen tetrahedron. It can combine in different ways. Most of the rock-forming silicates are composed of common elements combining with this tetrahedron, and they will, they can come in different ways. So you can have some of them will form as sheets. So those are going to be things like our micas, that they will then have cleavage that breaks into those sheets. They can form in rings. They can form into stacks. There's subgroups for how they come together. And so they have different strength between those bonds. So atomic bonds can create patterns repeating in 3D. So these are the building blocks of our crystalline structures. The mineral is a naturally occurring crystalline and abiogenic compound that is solid at room temperature and has a well-defined chemical composition. Physical properties such as luster, hardness, habit, cleavage, density, color, streak, etc. are the way that we identify common minerals, and our minerals are classed on the basis of their major anionic group. So remember, that's um, the negative ion. So rocks and the rock cycle. So minerals come together to form rocks. And then those rocks will move through the rock cycle, and we will have things changing and rearranging on the surface. So I will come back to this image. Basically, the rock cycle, you can take any rock and turn it into any type of rock. We will see that we have 3 types of rock. We have sedimentary rock, which are rocks that are formed from particles of other rocks. We have metamorphic rocks, which are rocks that are for other rocks that have been heated and pressed till they change into a new type of rock. And then we have igneous rock, which is a rock that is solidifying out of a melt, out of molten material. These 3 rocks can actually all go to each other, and we will talk about this more today. So a rock is defined as a coherent, naturally occurring solid consisting of an aggregate of minerals. So coherent means it holds together. Naturally occurring means it's not made by people. An aggregate of minerals means that we have many grains of minerals, sometimes different mineral species, sometimes the same mineral species. So when we look at this image, the image as a whole would not be considered a rock because it's not being held together. If you look at the individual pebbles, though, those are each rocks because we can see the different minerals in some of them, the different speckles, but they are being held together. If we pick them up, they are not going to break apart. So it's an aggregate of minerals. We can see these individual crystals that will interlock with one another. So here's an example of, again, we have these interlocking crystals. This is an individual crystal. It is not able to be separated out from the rest of the rock. So there are different ways to hold our minerals together to form rocks. We can have what are called clastic rocks. These are rocks where the grains are held together by some sort of a cement. And we can have crystalline rocks. So these are rocks where the crystals are interlocking with one another. Crystalline rocks will either originate as a mass, meaning they're solidifying out of molten material, or it happens when separate grains are welded together when they're still hot. We, as geologists, will call these soft rocks and hard rocks. Soft rocks are going to be clastic rocks. They're much easier to break. Crystalline rocks we call hard rocks. They are hard to break. I have tried to break off a chunk of a hard rock, a crystalline rock, and it has fought me back, and I've literally fallen down a hill with my rock hammer trying to break off a chunk. It was a volcanic rock. I eventually beat it, but it took a while. So we're going to start with crystalline rocks. So this is showing a crystalline rock, such as granite. If we zoom in on it, if we look at a microscopic image, we can see the individual crystals actually locked together like puzzle pieces. So that's what we're seeing here. If we draw this and expand these pieces out, we will see that they fit together perfectly because they grew together and then they froze together as they were coming out of a molten material. This is a classic example of a crystalline rock. Whereas the clastic rocks are where you have cement holding the material together. So here we have an example of sandstone. If we look at it under the microscope, we will see individual grains with space between them that's filled in by other material. So if we draw this out and blow it apart, we will see that the puzzle grains don't fit as closely together. We have actual cement, which is another material in between the grains, but we can still have space. So that's why they're easier to break. So when we're talking about rocks, we can talk about things either as bedrock, so that's rock that's still attached to the Earth's crust. That is what we're typically looking for when we're trying to talk about what's happened in a location. And we find this in outcrops. So outcrop is an exposure of bedrock. So if you just find a chunk of rock in your yard, that is not bedrock. That is not attached to the crust anymore. In order to find bedrock, you typically have to dig down a ways. When you drive along a highway and you see road cuts, that is actually cut through outcrops. So that is the actual bedrock. That's why we had to blast through it to make the road. So we have different types of rock. It's based on how it's formed. I mentioned this already slightly. So sedimentary rocks are formed by cementing together rock fragments. So those would be clastic rocks, or by precipitation of mineral crystals out of water solutions. So sedimentary rocks are defined as being parts of previously existing rocks that come together. Igneous rocks form by solidification of molten material. So you have fully melted material and then it cools and solidifies. Metamorphic rocks are where we have pre-existing rock is exposed to heat and pressure and it will change the rock without fully melting it into a new type of rock. I like to start with igneous rocks because, basically you think of it as the first rock. You're going from molten to actual rock. So you have molten material, which we see here, we see lava, and then we see our student is standing on rock that is formerly molten lava that has solidified into basalt in this case. So the difference between lava and magma is that lava is the molten rock when it's on the surface of the earth. Magma is the molten rock when it is within the earth. That is the only difference. This is the exact same material. So if we look at this cross section of a volcano, here we have a magma chamber. This magma then will then move up through the volcano and erupt as lava at the surface. It's the exact same material. It's just where is it found. So you have a magma cake until you cut into it and then it becomes a lava cake. So why is it hot inside the earth? Why can we have molten material inside the earth? There are sources of heat to the early earth. So we have remnant heat from when we formed the earth, all of those impacts during the age of bombardment, as well as just the heat of condensing the planet down. Early collisions with the planetoid that formed the moon. But we also do have a aspect of ongoing heat generation. So we have radioactive minerals. Those are those isotopes. And this actually generates heat. So there was a famous scientist named Lord Kelvin, who has a temperature scale named after him, who tried to calculate the age of the Earth by looking at the cooling of metallic spheres, and way underestimated the age of the Earth because Lord Kelvin didn't know about radioactivity at the time. He was before radioactivity had been discovered. So he didn't realize that the Earth was producing heat, not just losing heat. But Earth is slowly losing heat to space. It's losing that remnant heat. Even though we do have this ongoing heat generation, eventually Earth will cool down and die. So eventually Earth will solidify. So where does magma form? It doesn't form everywhere. We do not have molten material underneath all of the crust. We only have it in certain areas, which is why we have volcanoes in certain areas. If you remember from last week, volcanoes tend to happen on plate boundaries. So magma is not everywhere below the crust. Magma only forms in those special tectonic settings, typically plate boundaries. So we get partial melting in the crust and upper mantle. This melting is caused by different things. Remember, the mantle is solid, so we're going to partially melt it. So we can have a pressure release. This tends to happen at mid-ocean ridges. We can have volatile addition, so that's adding things that makes it easier to melt. This will happen at subduction zones. And we can have heat transfer, where we've just heated up material. This is what happens actually at hotspots. I will talk about all of this more when we talk specifically at volcanoes and igneous rocks. Not igneous rocks, when we talk about volcanoes in 2 weeks. So decompression melting is a reduction in pressure. So what happens is if you increase pressure, you need more heat to melt a material. By increasing pressure, you tend to reduce or increase the melting temperature. The same thing happens as well. If you decrease pressure, you reduce the melting temperature. The other thing you do is that the reason we have this increased pressure is typically that materials are at depth, so they're under a lot of pressure. At depth, remember, we talked about this last week, that in the crust, the temperature goes up 30 degrees per kilometer as you go down into the crust. So if you have things deep down, they are hot. The geotherm, remember? If we bring something to a shallower depth, especially if we do it fast, it will still be hot, but will be at a lower pressure, and it's easier to melt at a lower pressure. So the base of the crust is hot enough to melt mantle rock, but there's a lot of pressure there. So it's not melted at the base of the crust. But if we reduce the pressure but keep that temperature high, we can melt. So the pressure will drop when the rock is carried to shallower depths. So what we end up seeing is that we go from a geotherm that looks like this to one that looks like this, and suddenly we are able to move from that solid to the liquid stage. So this happens at mid-ocean ridges. So we have material is brought up to shallower depths. It's still hot, but it's now at a lower pressure, and therefore it's able to melt. This can happen with mantle plumes, so at hot spots. It can happen beneath rifts and at the mid-ocean ridges. We can also have what's called flux melting, which is addition of volatiles. So basically we put something into the rock that makes it easier to melt. Carbon dioxide and water, H2O, are two of the more common ones. So this will lower the melting temperature of a rock and make it easier to melt. Subduction will carry water into the mantle. The water is included in the minerals that are subducting. Once they get to a certain depth, they're basically pushed out of those minerals. That water then goes into the overriding plate and melts it, and then that melt works its way up to the surface, which is why we have volcanoes on the overriding plate. We can also have heat transfer, so we just heat things up. So rising magma will carry mantle heat with it. It will heat the nearby rock, melting it and incorporating it into the magma. It also happens at hotspots. Magma will have three components. So we have solids. So this is solidified mineral crystals that are carried in the melt. We have liquid, that's the melt itself. It will have mobile ions. And then we have the volatiles, which will be the gases that incorporate it in. Different mixes of elements yield different magmas. There are four major magma types based on the percentage of silica. So felsic is the most silica. It's silica rich. It is named felsic because it has feldspar and silica. The next one is called intermediate, which will make more sense when I tell you about mafic. I've already mentioned mafic chemistry. Mafic is magnesium and iron rich. It has less silica. So intermediate is called that because it's between mafic and felsic. And when we talked about the mantle, we mentioned ultramafic, so this is even more enriched in magnesium and iron and has less silica. To some extent, we can look at the colors of materials. So felsic materials tend to be light in color and light in density. Mafic materials tend to be dark in color and dark in density. And high density. So the magmas will vary chemically due to their initial rock composition, their source rock. So if you melt a mafic rock, you can get a mafic magma. If you melt a felsic rock, you will get a felsic magma. We can also have partial melting and crystallization. So partial melting means that as we're melting our rock, we're melting the things that are easy to melt first. So that will give us one magma chemistry. Partial crystallization means that when we are cooling our magma, we cool the things that are hard to melt first, which will change our magma chemistry. And then assimilation is where we melt the surrounding rocks and they get incorporated into the magma. So partial melting, upon melting, rocks will not melt completely. They will start to melt, and the things that melt first will be the easiest things to melt, the things with the lowest melting temperature. So that tends to be the more felsic materials. They have a lower melting temperature, so they will melt first. So we start off, the first things to melt will be those high silica materials because they have lower melting temperatures. So the melt part will have a very high amount of silica. It will basically be pulling out all the things that are those, more silica rich materials. If we're able to keep melting the source rock, eventually we will melt it all the way down, that it will have those more mafic materials in there. But we're always going to pull out as melt the silica rich materials first. So the silica-rich materials will melt first, the silica-poor materials melt last. So you can actually take a ultramafic rock and get a felsic magma out of it simply by only melting it partly. We can also, oh sorry, this is partial melting again, that we start off that our materials are, we're going to melt the silica rich. So this line is showing us the silica content of the magma. As we increase the temperature, we will start melting those more silica poor materials that are the more mafic materials, and so we will get increasingly mafic magma with increased melting. Fractional crystallization is the opposite of partial melting, so magma will change as it cools. So instead of with partial melting, the first things that will come out will melt will be the silica rich things because they have a lower melting temperature, they're easier to melt. With fractional crystallization, the first solids that will come out of the magma will be the things that are silica poor because they have a high melting temperature. They are hard to melt, they are easy to freeze. So once we start cooling the magma down just a little bit, it can no longer keep those things molten, so they will come out first. So these early crystals will settle out with gravity and they will sink to the bottom of the magma chamber. So the remaining melt will change its composition. So iron, magnesium, and calcium, the mafic minerals, will sell out first. The remaining melt will become enriched in silica, aluminum, sodium, and potassium. And then assimilation is the magma melts the wall it passes through, the rock it's passing through. The blocks of the wall rock, which are called xenoliths, can fall into the magma, and this will change the magma composition. You've added a new chunk of rock to it. We can understand how these things happen with Bowen's reaction series. So Bowen's reaction series describes the order in which minerals will melt or freeze. So the felsic materials, which are here at the bottom, they melt first and they freeze last because they are a low melting temperature. So when you are melting a rock, these will be the first things that become molten. The things that are ultramafic will be the last thing to melt. And when you are solidifying a rock, when you're freezing a rock, when you're crystallizing a rock, the first things to solidify, to crystallize, will be the ultramafic and mafic materials because they have a high melting temperature. The last things to crystallize will be the felsic materials. So as we crystallize, or as we slowly cool, our magma becomes more and more, silica enriched and more felsic. We have two types of series on here. We have what's called the continuous series, which is a mineral called plagioclase. There is a calcium-rich end member, and there's a sodium-rich end member. They have the same chemical structure. It's just we have calcium and sodium substituting for each other. The calcium-rich one will have a higher melting temperature than the sodium-rich one. And then we move into the more felsic minerals. The discontinuous series is where we have different minerals. So olivine is magnesium and iron silicate. That's as mafic as you can get. Pyroxene has a little bit of other stuff mixed in, a little bit of aluminum mixed in. Amphibole starts to have more stuff mixed in, as does biotite. Those were those two really messy chemical compositions that I showed you. And then we get more into those felsic materials again. So the bottom are the last things to solidify. The top are the first things to solidify. So magma will move because it will rise because it's less dense than the surrounding rock. The weight of overlying rock can also create pressure, which will squeeze the magma up, kind of like a toothpaste tube. How easily it moves is going to be governed by a property called viscosity, which is its ability to flow, or resistance to flow rather. Lower viscosity eases movement. So water has low viscosity, honey has high viscosity. So we see that higher temperature and lower silica content and higher volatile contents will have lower viscosities. So the hotter something is, the easier it is to flow. If you have hot chocolate in a jar and you heat that jar, that hot chocolate, or I'm not sorry, not hot chocolate, hot fudge. Hot fudge in a jar is almost a paste. If you put it in the microwave for a little bit, it will become able to be poured. So you raise the temperature. Silica is very sticky, so the more silica you have, the stickier it is, the less it will want to flow. The less silica you have, the easier it flows. And then volatiles tend to make things flow easier. You've broken up a lot of those bonds. The way a magma cools, or lava cools, is going to be dependent on the rate and the chemistry, and that will tell us what type of rocks we get. So whether or not it cools fast or slow is going to indicate the size of our crystals and the shapes of our crystals as well as our rocks. So if it cools fast, it will be small crystals, and they tend to be more planar. It will also cool faster if we have our magma more spread out. So for example, if we have a lava flow, that's going to cool faster than if we had a big blob. The bigger crystals are going to be due to slower cooling, and also the more we have, the slower it will cool. This is going to be controlled by depth, so deeper in the earth is hotter, so we're going to have slower cooling because it's still hot. Shallower is cooler, so it will cool faster because we lose heat faster. Deep plutons lose their heat very slowly. They take a long time to cool. They tend to be more blobby, more these big blobs, and they have bigger crystals. Shallow flows lose their heat more rapidly because they're spread out more. They tend to have smaller crystals and cool quickly. So spherical bodies cool slower, tabular bodies cool faster, which plutons versus flows. Groundwater can help remove heat. So if we have groundwater circulating around magma, it can help pull the heat out faster and cool it faster. So I'm going to introduce some words here that we're going to talk about when we actually start talking about igneous rocks in like 2 seconds. So intrusive or plutonic rocks. Intrusive means that it is inside the earth. Plutonic, it refers to plutons. This is an igneous mass inside the earth. So this is magma that intrudes. It cools beneath the ground. These have long cooling times. So they tend to have large crystals, which is called phaneritic. Phaneritic, remember, phanero means visible crystals. Extrusive rocks that extrude on the surface are also called volcanic rocks. This is lava that extrudes. It's magma that cools near the surface. It tends to happen at volcanoes. They have short cooling times, and they have small crystals, which are called aphanitic. The A in front means not visible. So igneous rocks are formed by cooling of a melt. So magma is melted rock beneath the ground. Lava is once that rock reaches the surface. Tephra are fragmented volcanic products formed during volcanic eruptions. So tephra is almost a sedimentary volcanic rock. Igneous rocks freeze at high temperatures. So anywhere from 1100 Celsius down to 650 Celsius, depending on their composition. So the mineral composition will reflect the magma composition. And then the texture. So we're going to describe our igneous rocks based on their composition and their texture. The texture will reflect the cooling history. So igneous compositions, we have those felsic rocks, which is rich in silica, intermediate rocks, mafic rocks, which is more rich in iron and magnesium, and ultramafic rocks, which is almost entirely those really dark, heavy minerals. So the two major categories are, again, intrusive and extrusive, which is based on their cooling locale. So extrusive settings cool at or near the surface. They cool rapidly. They have small crystals. These are volcanic rocks. Intrusive settings cool at depth. They cool slowly. The crystals grow large, and these are plutonic rocks. We will have a name for the extrusive rock or the aphanitic rock and the intrusive rock or the phaneritic for each composition. So crystalline textures, we have aphanitic, fine-grained. These are going to be our extrusive rocks. Rapid cooling, the crystals don't have time to grow. They generally need a microscope to see the crystals. Phaneritic, which are coarse-grained rocks, will have a slow cooling time. The crystals have a long time to grow. They're intrusive. The grains are about equal in size, and they're easily visible. So we combine the texture and the composition to get our different rocks. So for the felsic composition, the aphanitic rocks would be rhyolite, the phaneritic rocks would be granite. For intermediate composition, the aphanitic rocks would be andesite, the phaneritic rock would be diorite. And then for mafic, the aphanitic rock would be basalt, and the phaneritic rock would be gabbro. There is an ultramafic rock that the phaneritic is called peridotite. The aphanitic is komatiite, which is no longer seen at the Earth's surface. I like this chart a lot. There's a lot of information on here. I want to point out these names are the simplified, very basic names. There are a lot more complex naming structure for igneous rocks. So this chart is going to show us the density on this red. So we go from low density to high density. The temperatures are this arrow, so we have low temperature eruptions to high temperature eruptions. That's also the melting temperature. And this blue arrow is the silica content. This one goes in the opposite direction, so we go from low silica to high silica. Then we have the texture, so fine versus coarse. Inside these boxes are the names. So again, that komatiite and peridotite are going to be our ultramafic. And then this side over here, we have the colors indicate the different compounds, and we have rhyolite, andesite, and basalt, which are our felsic, intermediate, and mafic. Silicic is another way of saying felsic, I might add, rocks, and we see the percentage of the different compounds for each rock. So we see rhyolite has a much higher percentage of silica, has a lot of aluminum. We don't see nearly as much of the, well, actually, no, we don't see. Oh yeah, we do see a little bit. So the magnesium is this dark blue and the iron is the green, but we don't see nearly as much as what we see in these more mafic rocks. So basalt will be our mafic rock. We see that the silica's gone down. We see a heck of a lot more of our iron and magnesium. We see similar amounts of aluminum across all three. Similar amounts of sodium. We see less potassium. Potassium is a very felsic mineral. Composition. So these will show us the variations in the chemical content, and then this column here is showing us the actual minerals. So this is basically the Bowen's reaction series plugged on here. So peridotite is almost all olivine. Basalt has some olivine, some pyroxene, a little bit of amphibole, and maybe some of that plagioclase. Intermediate compositions have not, we no longer have the olivine. We're starting to bring in a bit of maybe biotite, and then when we get up into the felsics, that's where we're going to get our quartz, our plagioclase, our sodium, and member of the plagioclase, we're getting the biotite. These are going to be the lighter minerals. So now I'm going to quickly go through each of these different rock types. So I'll start off with ultramafic. If we have a phaneritic texture, it is peridotite. It's primarily olivine with maybe a little pyroxene. It's not common at Earth's surface, but it is basically the mantle. It can produce mafic magmas by partial melting. Mafic rocks are where we have olivine and plagioclase and pyroxenes. If it's aphanitic, it's basalt. If it's phaneritic, it's gabbro. This is the ocean floor. This is what makes up our ocean crust. Intermediate rocks are where we're getting more things like pyroxenes and amphiboles and plagioclase. If it's aphanitic, it's called andesite, named after the Andes. If it's phaneritic, it's called diorite. So in this case, plagioclase is going to have our sodium and calcium substituting pretty much equally for each other. And then finally we have felsic. So felsic is where we're going to have quartz, we're going to have the sodium feldspars, we're going to have the potassium feldspars, biotite. So if it's aphanitic, it's called rhyolite. If it's phaneritic, it's called granite. We can also have obsidian, which is a special case where we have primarily SiO2 and we have glass. So the high silica content tends to make things very viscous, so we tend to have very large eruptions with this type of material. So not all magma is created equal. The different chemistry leads to different types of volcanoes. I will return to this when we talk about volcanic rocks, or when we talk about volcanoes themselves. So the more silica, the lower the temperature, the higher the viscosity, the higher the volatile content, the more explosive our eruptions are going to be. So rhyolite and granite, our felsic materials, tend to be very explosive. They have a low melting temperature, they have a high viscosity, and they have a high amount of volatiles. Whereas basalt and gabbro, our mafic rocks, have high melting temperatures, low viscosities, not a lot of volatiles, so they tend to be not very explosive. So the chemistry is really going to control what type of volcanoes we get. And again, I will return to this. I believe I show this exact same slide when I talk about volcanoes. So the next rock type I like to talk about is sedimentary rock. So the sedimentary rock is formed by cementation or precipitation. So we're basically forming a rock by particles of other rocks. So 85 to 90% of mineral products come from sedimentary rocks. Gas, coal, groundwater, sand, gravel, concrete. They're very common. So 75% of the continents, 99% of the ocean floor. Now, when I say 99% of the ocean floor, I'm talking about the stuff on top of that basaltic crust that's being created at the mid-ocean ridges. So there's layers of rock sitting on top of that crust. This represents the ancient Earth. So layers record the environmental conditions present during their formation. So we define 4 classes of sedimentary rock. So we have clastic or detrital. So this is where we have loose fragments of rocks that are cemented together. So sandstone would be an example of this. Biochemical, so we have cemented shells of organisms. So this would be things like limestone. Organic, so this is carbon-rich remains of once living organisms. So that would be like coal. And chemical, so this is minerals that crystallize directly from water. So this would be like salt beds and things like that. Those would be like those evaporate type things. And some limestones will fit into that too. So physical and chemical weathering provide the materials for sedimentary rocks. So we basically have to break down our rocks to get the particles before we can make new rocks. So we have to weather away, break down prior rocks. So the way that we form sedimentary rocks is first we have to generate detritus by disintegrating a previously existing rock. That's called weathering. Then we have to remove the sedimentary grades from the remaining rock, and that's erosion. Then we have to transport, typically by gravity, wind, water, and ice, that material to then be deposited. So we have to settle out of the transporting medium into a new location. And the final step is lithification, which is where we're going to turn that sediment into a solid rock. So mechanical weathering is we're physically breaking rocks apart. So there's a lot of wedging involved in this. So frost wedging is the same thing that happens in potholes. This is where water gets into the gaps in rocks. It then freezes. When it freezes, it expands, and that pushes the rocks further apart. Salt wedging is the same idea, only now we're going to precipitate salt into the gaps, and when that salt precipitates, it pushes apart. Root wedging is where a plant grows into a crack, and as the roots expand, they will push the rock apart. The idea is always something is in the crack pushing the rock apart. Chemical weathering is where we are going to be dissolving the rock away with breaking up the rock's chemical bonds. And so this happens a lot with water coming through, and that you are dissolving away the rock, but you're having some of the bonds breaking up, and then you disassociate the elements into their the compounds, the minerals, into their individual elements, and then it's transported. Chemical weathering is aided by physical weathering because the more surfaces you have, the easier it is to break things apart. So as we break our rock into smaller pieces, there are more faces to be acted upon. The more faces to be acted upon, the easier it is to break it up, and also the easier it is for chemical weathering to act on it. So we also tend to see things getting more rounded with time. the first parts to be broken up will be these sharp corners. The more sharp corners we have to break up, the easier it is to break those up. And again, the more surface areas we have, which the smaller pieces we have, the more small pieces we have more surface areas, and so it's easier for chemical weathering to act on it. So sediment will be moved away from its parent rock. Maturity is how much processing that sediment has undergone. So we can have textural maturity, so that's how much rounding, so how much we've gone from an angular clast to rounded clasts, and sorting, so how similar in size are the sediments. And mineral maturity means that how much of the unstable minerals have been removed. So a mature sediment is going to have very similarly sized clasts that are all rounded and all have similar chemistry. Time and transport will cause sediment evolution. So with time and transport, so with time and distance, the average grain size will go down and the amount of rounding and sorting will go up, and the composition will change. The unstable minerals will go down and the stable minerals will increase. So we will see that a mature sediment will be very similar looking, all samples of it. So the class size is the size of the grains. They range from very coarse to very fine. So we can talk about them as boulders, cobbles, pebbles, sand, silt, and clay. Gravel is coarse grain sediments. Mud is fine grain sediments. As distance increases, grain size decreases. We have more time to break it up. We break it up more. Sorting is how similarly sized the fragments are. So a poorly sorted sediment will have various sized grains. We'll have some small ones, some big ones, and everywhere in between. As it gets more well sorted, we will end up having all similarly sized grains. And then angularity or roundness, we start off with a lot of sharp edges. Those are the things that are going to get broken off first and attacked first. So it will become more and more rounded with time and distance. Lithification transforms that loose sediment into solid rock. So it has a couple steps. Compaction will, as we bury more and more sediment, it adds pressure to the sediment. It squeezes out air and water and will compress the grains closer together. And then we have cementation. So we will have minerals growing in the pore space. So that's the space between grains. It often is either quartz or calcite. It will precipitate out from the groundwater and it will basically glue the sediments together into a rock. So there are different types of clastic sedimentary rocks rather. So here we have an example of breccia. Breccia are large angular fragments that are cemented together. It means that it was fairly close to its source material. It didn't get transported very far. An example would be talus under a cliff face. So this is what the individual sediment would look like before it's lithified, and this is what it looks like as a rock. That it is, big chunks that are not well sorted that are cemented together. A conglomerate is similar to a breccia, only now that we have more rounded clasts. So they're still very coarse. They're big clasts. So flowing water will wear off the corners of edges. So these tend to be river channels. They are deposited a little bit further from the source than breccia would be because they're rounded, but they're still not well sorted. So here we have an example of a pebbly riverbank, and here we have an example of one of these conglomerates that is lithified, that we have these big clasts that are cemented together. Arkose is a type of rock that is sand and gravel with lots of feldspars, so it's a very pinky red color. They're very common in what are called alluvial fans. This is where you have you have a river pouring out into a flat area, and as it moves from its channelized flow in the mountains to this flat area, it spreads out and then it loses all of its energy, so it will drop everything it's transporting. Because of this, we have fairly short transport conditions. So basically, it didn't get very far, it didn't get very sorted. It just all dropped as it hit the mouth of this flat area. These alluvial fans also tend to happen in arid conditions. These arkoses tend to show short transport and more arid conditions. So here's an example of the rock. And we can see it's poorly sorted. We have this huge clast, some smaller clasts. Sandstone is a clastic rock made of sand-sized particles. It's common in beach and dune settings. Quartz is the most common mineral in sandstones. The They're a very common rock. It's sand compressed into rock, and we can actually see what's called cross bedding, so we can see the individual planes of the layers of sand. Mudstones and shales are silt and clay, so they're very fine-grained particles. This is quiet water settings, so floodplains, mud flats, deep oceans. So these are well sorted, and they have to be very calm environments for these very fine-grained particles to settle out and to lithify. So here's an example where you see shale and sandstone intermixed. So we're basically seeing going between the beach environment and the shallow mudflat environment. Biochemical sedimentary rocks are derived from the shells of living organisms, so plankton, snails, etc. The hard mineral skeletons will accumulate after death. So if we have calcite and aragonite, it will become limestone. We can also have opaline silica, which would be chert. So it depends on what was in the skeletons. So limestone is a sedimentary rock made of calcium carbonate, calcite or aragonite, which are polymorphs, mean they're the same chemistry, different shapes. Limestone commonly preserves fossil organisms, and it is found from oceanic environments. The deep oceans can make a type of specific type of limestone that is called chalk. It is made from calcite skeletons of unicellular organisms called coccolithophoros. And so here we have, this is what these skeletons look like. These are the cliffs of Dover. We can have very, very fine-grained limestone called micrite that forms in the deep oceans. So this is a skeleton of deep-sea plankton. So we can have limestone forming basically everywhere within the oceans. In the deep oceans, we can also have opaline silica that's formed from oozes. So the deep oceans have very quiet environments, so they can have clay deposition. They can also have these oozes. They can have calcite above 3,000 meters depth, so those are those coccoliths. But below that, we will have silica, so we'll have the chert. So this is the very, very deep oceans. So calcite will dissolve at these very great depths, so only silica-based skeletons survive. So opaline silica of marine plankton. This can be in pore fluids and solidify into a gel. The silica gel precipitates chert as nodules or beds. So this is what is used a lot of times as like fire starters, chert, or for arrowheads. So those are some of the examples of sedimentary rocks. There are many, many, many more examples of sedimentary rocks. I'm highlighting a few. The next one I'm going to talk about are metamorphic rocks. Metamorphic rocks form from a pre-existing rock that is going to change due to changes in temperature and or pressure. So if you heat it and apply pressure to it, it can change. So they are formed from solid state recrystallization of pre-existing rocks due to changes in temperature and pressure, or composition of pore fluids. So they can form from igneous, sedimentary, and other metamorphic rocks. It typically will erase original diagnostic features. So you're basically starting fresh. They form deep within the crust. They're not as abundant at the Earth's surface, but we find remnants in the deep crust, particularly in the core of mountain belts, modern and ancient. So there's a lot of metamorphic rocks, say, in Canada. They only form under particular conditions. We need extreme pressure and temperature. So when we talk about metamorphic rocks, we talk about what's called the protolith. The protolith is the original rock before metamorphism occurred. And then we add meta to that rock to indicate what our metamorphic rock is. So a metabasalt is a metamorphosed basalt. We will have new minerals forming in response to changes in temperature, pressure, and pore fluids. The grains are recrystallized at about the same time, so we get textural changes. The new minerals will grow in the direction of lowest stress, so they will be perpendicular to pressures. So if we are squeezing our rock, the minerals will grow opposite to the direction that we're squeezing. So those grains will always take the path of least resistance. So if the stress is vertical, if we're pressing, the grains will grow to the side. So changes in temperature, minerals become unstable and react with other minerals, and so we create a new new mineral assemblages that are equilibrium with the new conditions. So the crystal structures break down and they're recreated with new ions and atomic structure, so we get new minerals. For changes in pressure, as we increase pressure, we reduce the space occupied by the atoms, so this will drive chemical reactions and create new minerals. So mineral composition indicates the temperature of metamorphism and the pressure of metamorphism. Different minerals are in equilibrium at different temperatures. Certain minerals will only appear in certain pressure temperature environments. So for example, high pressure, low temperature is a very specific environment. That's the environment that this mineral kyanite forms in. So this is high pressure, this is low temperature. The only place we have that situation are subduction zones, where we will push a plate down to depth very quickly and it doesn't have a chance to heat up to the equivalent temperature of that depth. So when we see kyanite, we know that we had a subduction zone, for example. These three minerals, kyanite, sillimanite, and andalusite, are all the same chemistry. They are an aluminosilicate, but they form in different conditions. So depending on which one you see, you know what the pressure temperature conditions that rock formed in were. Metamorphism will change the mineralogy. For example, you can go from a shale, which is a mudstone made of quartz, clay, and iron oxide, to a rock called a gneiss, where we will have quartz, feldspar, biotite, and garnet. So we can change the mineralogy. We rearrange the elements from the protolith, so new minerals will grow. The new minerals are made of the same elements as the old minerals, unless we brought in something new with our pore fluids, but we're rearranging those those elements into new minerals. We can also change the texture, so we will go from, say, a clastic rock to a crystalline rock. So we will have intergrown and interlocking grains. And this happens in different types of environments. So we have different types of metamorphism in these different environments. I'll go through most of these. So I think I go through all these. So contact or thermal metamorphism is where you just heat the rock. It's typically due to magma, so you have molten rock close by, and so you will essentially cook the rock that's in contact with that hot igneous material. Here's an example where we can basically see that if we were looking at this as an analogy with pottery, that porcelain, which is very high temperature firing, would be found closest to the heat source. Then we would move into pottery, then brick, and then clay at the far side. So basically the highest temperature rocks will be closest to the intrusion, and then we will get progressively lower in temperature, which is called grade, lower grade metamorphism as we move further away. Burial metamorphism is basically the more weight you drop on top of material, the more pressure you have. Also, as you bury it, it's getting deeper, so it gets increases in temperature due to the geothermal gradient. So this is by far the most common metamorphism. This happens just from burying more and more sediments on top. This happens regionally. Dynamic metamorphism is where we are breaking rock at a fault zone. So we are sliding rocks past each other, and in that fault zone we will have very localized metamorphism. Depending on where it's happening, we will have different types of behavior. So in the shallow crust, the upper 10 to 15 kilometers, the rocks behave in a brittle fashion. They break. So we will crush our mineral grains and form what's called fault breccia. Deeper in the crust, so below that 10 to 15 kilometers, the rocks are more ductile, so they behave more like taffy, and that will form a rock called myelinite. So it will have very tiny grains that will be stretched out parallel to that fault zone. Regional metamorphism is tectonic metamorphism. So this is where we have directed compression in mountain building events. So the rocks get caught up in the mountain building events when we have two plates coming together. So they're heated because of the geothermal gradient that they're being buried. They're also being smashed and smeared by differential stress, that they're just having these two plates pushing into each other. Um, so this can form mobile belts that are hundreds to thousands of kilometers long. Um, so the directed compression smashes pre-existing rocks and buries them deeply where they are heated by the geothermal gradient and plutonic intrusions. The heat and pressure of orogenesis, or mountain building, creates huge volumes of metamorphic rocks, more than any other mechanism. So I was a little bit wrong when I said that burial mechanism is the most common. Hydrothermal metamorphism is alteration by hot, chemically aggressive water. So it's a dominant process near mid-ocean ridge magma. So cold ocean water seeps into the fractured crust. We heat that by the magma that's coming up. The water then reacts with the mafic rock. The hot water rises and is ejected via the black smokers. So this causes a lot of metamorphism in the crust right at mid-ocean ridges. So this hot, chemically aggressive water chemically alters the basalt. The process starts when cold ocean water seeps into fractured crust. It's heated by magma. The water then reacts with the mafic rock and is ejected at black smokers. The mafic rock is metamorphically altered. Subduction metamorphism creates a very unique set of rocks. They're called the blue schist facies. So this is a low geothermal gradient. So we have low temperatures and high pressures. They're ideal conditions for a rock called glaucophane, which is a blue amphibole mineral, or kyanite, which is the blue aluminosilicate. So because we have these blue minerals, we call it the blue schist facies. And then we have shock metamorphism. So periodically Earth gets hit by an object. The impact generates a compressional shock wave, and we have extremely high pressure. We also have a lot of heat that vaporizes or melts large masses of rock, and so we have specific high pressure minerals that are only forming in these situations. So there's some very specific forms of silicates. So quartz will become either coesite or shishovite. It's SiO2, but it's in a different form. So depending on what the pressure temperature conditions are, we will get different metamorphic rocks. And so we basically record what conditions these rocks underwent. We call this the grade of metamorphism. It's defined by how much pressure and temperature have been applied. Contact metamorphism comes from high temperatures and low pressures. So this is a lower we go from low grade to high grade. Blue schist is high pressure, low temperature. And then we have the normal temperature pressure, where we really talk about this low grade to high grade change. And if we go too high, it melts and then it moves into the igneous rock range. Metamorphic textures form due to a thing called differential stress. So that means that we have stress that's greater in one orientation. So we're squeezing or stretching. Deformation will reorient mineral grains and form new textures. So before, we will have just random orientation of our grains. After we have compression, we will form what's called foliation, so we have an alignment of those mineral grains. We can also have an alignment if we are shearing, so we're sliding rocks past each other. So basically, foliation is where the rocks line up. So the difference between differential stress and other types of stress are called uniform stress, or hydrostatic or lithostatic stress, where we have all the same amount of stress, and so we only have changes in volume. Differential stress means that in one direction we have a different amount of stress, hence differential, and so we will have this reorientation of materials. So an example of a foliated rock would be slate. So we will start off with shale. It's a type of clastic sedimentary rock. As we metamorphose it, it will actually crystallize and realign into these weak planes that are cleavage planes, so planes of breaking, that will be perpendicular to the amount of stress. And so that's why we use slate, because it breaks, it cleaves so nicely. We use it to make roofs and also chalkboards and pool tables. So it will break along those foliation planes. So slate is a fine-grained, low-grade metamorphic shale. It has a distinct foliation called slaty cleavage. That cleavage forms perpendicular to the compression through the parallel alignment of clay minerals in the rock. Cleavage is not often aligned with bedding planes. This foliation produces a weakness in the rock, which allows it to be split along the cleavage planes to produce tabular slate shingles that are great for roofing. The next step up, if we apply a bit more heat and pressure, is called a phyllite. So it's fine-grained, mica-rich rock that forms by the metamorphic alteration of slate. Phyllite has a silky sheen called a phyllitic luster. So the clay minerals in the slate protolith neocrystallize into tiny micas, which gives it the shiny appearance. With further metamorphism, phyllite turns into schist. So schist is a fine to coarsely grained crystalline rock with larger micas, indicating medium to high grade metamorphism. It has a distinct foliation from those large micas called schistosity, so we can see the layers. Common minerals would include muscovite, biotite, quartz, feldspar, kyanite, garnet, starlite, and amphiboles. And then if we keep going, we will have what's called compositional banding. So this can develop as we increase our metamorphism. So basically we will start to have our minerals migrate into bands of similar compositions with increased metamorphism, and those bands will be perpendicular to the compression. So we can have a mafic band, which would be the dark, and then a felsic band, which would be the light, and then mafic band. We call this gneissic banding. So during solid state differentiation, chemical reactions segregate light and dark layers to create this compositional banding. So when it's extreme, we call the rock a gneiss. Gneiss has distinct compositional bands composed of light bands of felsic minerals, so quartz and feldspars, alternating with dark bands of mafic minerals, biotite or amphibole. So if we take a shale protolith, we call this the pellitic series. If we start off with shale, if we go through the typical regular regional metamorphism, the low-grade metamorphic rock would be a slate, and as we increase our metamorphism, we will go through schist, gneiss, and then a migmatite is a highly metamorphosed gneiss. If we go through the blue schist facies, we will, in a subduction zone, we will get a blue schist. It's called a schist because it is a schist. We can also have a burial metamorphism that makes a rock called a hornfels. If we don't have differential stress, we create a texture that's called equant, meaning that we have the same materials in all directions. So this is a non-foliated texture. This happens if we had the metamorphism of a parent rock that's predominantly composed of one mineral. So sandstone and limestone are the two most common. So if we start off with limestone, we will make marble. Marble is a crystalline limestone. It's non-foliated, so there's no fabric evident. They lack minerals to align into a fabric. If we start off with a sandstone, we make a rock called a quartzite. Again, quartzite essentially looks like crystalline sandstone. So I like to talk about countertops. Most natural stone countertops are actually metamorphic rocks. They're more impressive looking. Quartzite is one of the better rocks to choose for a countertop, but the prettier quartzites mean that they have more impurities in them, so they're actually weaker. When my parents were picking out their countertop, they kept asking me my opinion, and I kept saying, you don't want to know my opinion. The boring rock is the one you should pick. They did not pick a good quartzite, they picked a pretty quartzite. Honestly, it doesn't really matter that much, they're all hard, but yeah, most quote granite countertops are not granite. So metamorphic grade is the intensity of metamorphism indicated by the type of rock, which is going to tell us our pressure temperature conditions. So we have low grade to high grade. Metamorphic facies is the set of mineral assemblages that indicate a certain range of pressure and temperature. So blue schist facies tell us that we have the pressure temperature conditions for the subduction zones. So if we want to classify metamorphic rocks, we are going to look for the protolith and the metamorphic grade using index minerals. Texture can be important, so increasing foliation indicates an increased metamorphic grade, but it doesn't always perfectly match. So if we start off with the mafic series, we start off with basalt. If we go through regional metamorphism, we will go into the green schist facies. Then we will go into the amphibolite rocks and finally get into more of our migmatite rocks. Whereas if we go through the blue schist facies, we will go into blue schist rocks and then into a rock called an eclogite. So if we look at a basalt protolith, and we go through the green schist pathway, so this is where we have similar pressure temperatures. In the green schist rocks, we're going to have a lot of chlorite. In the amphibolite facies, we're going to have a lot of hornblende. In the granulite facies, we will have garnet and pyroxene. If we go through the blue schist facies, so this is the lower temperature, higher pressure, we will have a lot of glaucophane in the blue schist facies. The eclogite, which one of my professors referred to as the Christmas tree rock, has a green pyroxene and garnet, so it's green and red. The shale protolith, the Politic series, I've already talked a little bit about this. Again, we go through slate, schist, gneiss, migmatite. So if we start off, if we're going through the green schist facies, so we're going through basically increasing, similar pressure temperature. We have a lot of chlorite again in the green schist, and the amphibolite we're going to have garnet and biotite schist. So these big chunks are garnets, and then the granulite will be our gneissic texture, and then we can get to a migmatite. If we go through the blue schist facies, now we're going to have more kyanite instead of the glaucophane. If we go through our carbonate series, we start off with limestone, we will make marble. It doesn't really matter where you do it, it's always going to be marble. So you start off with metamorphic, non-metamorphic is the limestone, and you will have marble. Quartzite series, we start off with sandstone, we get quartzite. Doesn't matter where you're at, your metamorphic rock is going to be quartzite. So now I want to talk a little bit about the rock cycle just to bring it all back together. So the rock cycle is this idea that we take the same materials that we've had on Earth for 4.6 billion years, and we're just recycling them. So if we melt it all the way down, we will have an igneous rock. If we remelt that igneous rock, it will become a new igneous rock. If we heat that igneous rock and add pressure to it but don't melt it, it becomes a metamorphic rock. If we break it up and let it reform, it will become a sedimentary rock. That sedimentary rock, if we melt it, it becomes an igneous rock again. If we heat it, it will become, but no, don't melt it, it can become a metamorphic rock. Or if we just break up that sedimentary rock and keep resorting it and transporting it, it will become a more mature sedimentary rock. Metamorphic rocks, if we melt them all down, they become igneous rocks. If we heat them but don't fully melt them, they just become more and more metamorphosed, or they can be broken up and then sent into the sedimentary cycle as well. So basically the rock cycle means that we can be continuously recycling these rocks. We also have the Wilson cycle. So the Wilson cycle again is this process of opening and closing oceans, creating supercontinents, and having periods where we have more but smaller continents. We are also in the process creating metamorphic rocks, we're creating igneous rocks, and we're creating sedimentary depositional areas. So we create areas where we can have, our volcanic rocks are going to be our igneous rocks. We will have sedimentary rocks forming in these low-lying areas. We will have metamorphic rocks happening where we have the compression, where we have alteration at mid-ocean ridges, things like that. When we finally have our continent coming back together, we will have massive amounts of metamorphism in that regional mobile metamorphic belts. And then when we start breaking the continents apart again, we'll have additional igneous rocks. So the Wilson cycle is basically we're making these different types of rocks in different environments. And I've already discussed the Wilson cycle as being this idea of bringing together supercontinents and then breaking up into smaller continents. We talked a lot about that last week. So this cycle is being driven by the plant's internal heat, the gravitational field, and external heat. So external heat being energy from the sun. So the plate movement causes uplift of mountain ranges. This will expose rocks to weathering and erosion. This will produce sediment. Weathering and erosion is going to be driven by gravity as well as that external heat from the sun. Plate motions generate the metamorphic settings and melt rocks that are brought to the surface through volcanoes and uplift. Solar heat is going to cause weathering, and erosion. And then life will also impact the atmosphere. It will speed up weathering. It will build reefs. It can also help break up rocks some more. So again, this week has been fairly long. I apologize, there's a lot of material. We also are doing 2 labs. We're going to be looking at minerals in lab, and then you will be doing the rock cycle on your own. I will show you the pre-lab videos for both of these. Together, I think they're about 20 minutes. So let's do minerals first.
Hi there, this is Callan Bentley. Welcome to your first pre-lab video. This week in lab we're going to be taking a look at minerals, and specifically how we tell minerals apart using their different properties. We're going to take a look today at stuff and think about the stuff that surrounds us on a daily basis. So if you look around your home or your lab, wherever you're watching this video, you'll notice that you're surrounded by various materials. If you look in the background behind me, you can see I'm surrounded by wood, which obviously comes from trees. That's not a mineral. But depending on your location, you may have some glass in your immediate field of view. That glass does come from a mineral. It comes from quartz. You may be surrounded by drywall. Drywall is a building material that's made out of another mineral called gypsum. You're going to be able to tell different minerals apart by the end of today's lab, and this may sound like a big complicated task, but in fact it's going to use some pretty simple materials, some pretty simple tools. You're going to be looking at minerals in the context of whether they can be scratched by a nail or whether they can scratch glass. A penny will be one of the tools you use today, even your own fingernails. We'll also be using a magnet. And then you'll be using all those different tools in the context of the mineral identification key in your lab manual. That will allow you to figure out which mineral is which, and therefore what human uses that mineral is good for. Let's take a look. Remember the relationship between minerals and rocks. This is an example of the rock known as granite, and you can see that there are different colored patches to this granite. Those different colored bits are minerals. For instance, the gray colored bit right there is quartz, the black colored bit right there is hornblende, and that pink stuff that's so prominent, that's feldspar. So we're going to be focused on the minerals today so that in later labs we can learn how to use the minerals to identify rocks. Which of the 4 items on the screen are examples of minerals, and which of the 4 are examples of rocks? Take a second to consider this. Well, hopefully you noticed that this one right here and this one right here have a distinct crystalline form. Obviously, the actual crystals look very different. One is transparent, one is metallic, one is sort of prism-shaped, and one is cube-shaped. But those are examples of minerals. The other examples, like this thing here and this thing here, those are examples of rocks, and you can see that many different individual crystals that make up those rock specimens. So we are not focused on those today. Mineral specimens is their color, and this is useful, but I don't want you to depend too much on it. For example, all the minerals you see here in front of you are varieties of quartz. There is a milky kind of quartz, there's a smoky quartz, a sort of orange colored quartz, and a purple colored quartz, but they're all quartz. So the color alone isn't going to be sufficient to identify the minerals. Here are examples of the mineral fluorite. You can see that there are a bunch of different colors. One thing you'll notice that they all have in common, though, is they have a similar shape. So that shape is something that is more important. It's referred to as mineral habit. And so some examples of mineral habits are illustrated here on the screen. You can see there's a large variety of different habits, from a cubic sort of shape like you see down here in the lower right, to a spray of sort of needle-like mineral crystals. And then you can even have a mineral form that is fibrous, and we call that asbestos. Another characteristic of minerals is how they reflect light. Some examples of that are shown here on the screen. One of the most obvious differences in the way that minerals reflect light are some minerals reflected in a metallic fashion. So in this image here we've got galena and native copper. Both of them look like metals. Obviously, one has more of a coppery tone and one more of a silvery tone, but they both reflect light in a metallic way. Other minerals have a more earthy luster, so they kind of look like dirt. Others have glassy lusters or opalescent lusters, satiny or waxy lusters. And a lot of those are a little bit more subtle than the metallic-non-metallic difference. One thing that you'll really be able to rely on this week in lab is your assessment of mineral hardness. Minerals are classified in terms of their relative hardness on a 10-point scale that runs from the softest mineral known, talc, up to the hardest mineral known, diamond. You're going to evaluate the hardness of minerals, their resistance to being scratched, using substances of known hardness. So one of those is going to be your fingernails. So hopefully you brought your fingernails to class today. You will also be using a copper penny, wire nails, a harder piece of metal like a knife blade or a masonry nail, and then there's a streak plate as well. Some labs will also use glass. Glass is about the same hardness as the knife blade, about 5.5 on the Mohs scale. So how's this work? Well, basically go and try and scratch the mineral. Start with either the hardest or the softest and then work your way towards the other end of the scale, and eventually you'll get stuck somewhere in the middle. So for instance, say you had a mineral that was so hard it could scratch your fingernail and it could scratch a copper penny, but it was not hard enough to scratch a wire nail. So the wire nail would be harder than the mineral. That would mean that the mineral's hardness falls between a 4.5 and a 3.5 on the Mohs scale of hardness. One example mineral that falls into that range.
Let me just interject here. When you're doing this, please do not, when you're testing your fingernail against the mineral, don't try to scratch your own fingernail with the mineral. See if you are able to scratch the mineral with your nail. So use your nail to scratch on the mineral. Don't try to, rub grooves in your own nail. I saw people doing that last term and it gave me the heebie-jeebies. You don't want to be cutting into your own nail. So just see if you're able to impact the mineral with your nail. And I will let him get back to it.
Range is the mineral fluoride. So here's an example where we've got two minerals and we've tried to figure out which one is harder. Basically all you have to do is grind them against one another, and whichever one succeeds in scratching its neighbor is the harder of the two. So in this case, sample B would be harder because it scratched sample A. Another technique that you'll be using this week in lab is streak. You're going to have a little square piece of porcelain which is called a streak plate. That's this thing right here. And what you're going to do is rub your mineral specimen against that streak plate. It will leave behind a powdered form of the mineral, and the color of that powdered form of the mineral is diagnostic for figuring out which mineral it is. So in this case, you've got a mineral with a distinctive golden metallic luster, but it leaves behind a blackish streak on the streak plate. What's curious here is that the streak color is actually far more reliable than the color of the mineral specimen itself. One mineral that's particularly tricky, but it can be teased out with the benefit of the streak plate, is hematite. You can see here that hematite comes in both a non-metallic and a metallic form, but they both leave behind a brick red streak on the streak plate, so you can rely on that. Another characteristic of minerals is how they break. Some minerals break with an irregular fracture. Other minerals break with a so-called conchoidal fracture. Irregular fracture is just like what it sounds like. It's irregular. Conchoidal fracture is pretty distinctive because it's sort of a scoop-shaped fracture, often with little ribs that run along it. Its overall shape is something like a clamshell. Other minerals have weaknesses within their crystal lattice that allow them to break more easily in some directions than in other directions. This is referred to as cleavage. Up here in the upper left we have an example of mica. Mica is a mineral that has one plane of cleavage, and it breaks very cleanly in that one direction and that one direction only. Other minerals have two planes of cleavage, like this one right here and this one right here. In the example in the middle, the two planes of cleavage intersect at a 90-degree angle. So that angle right there is 90 degrees. Whereas over in this example here, you can see the angle is far wider than 90 degrees. So that's a non-90 degree angle intersection between those two planes of weakness. Other minerals have three planes of cleavage that can intersect at 90 degrees, or three planes of cleavage that don't intersect at 90 degrees, or even four planes of cleavage. All of those are possibilities. Here's another example. This is sort of a distinctive thing that you'll find on a very few minerals. It's called striations. On certain planes of cleavage of plagioclase feldspar, you'll see these little tiny lines that run across the surface of the cleavage plane, but you'll be able to see them if you tilt the mineral back and forth in the light. Another example of a distinctive property that doesn't apply to most minerals but does to a few is the property of being magnetic. Magnetite is a nice example of a mineral that has the property of being magnetic. Another property that's very distinctive and will cue you in instantly as to which mineral you're dealing with is the reaction to acid. You will have in lab some dilute hydrochloric acid, and if you put a drop of that,
You will not be playing with acid in lab. We do not do that with just safety rules. So, unfortunately, you can ask me if it would fizz. You can also ask me if it will taste salty, but you will not test those yourself.
on the mineral calcite, it will immediately start fizzing in a fairly vigorous fashion. So bubbles will be produced and it will be giving off carbon dioxide gas. Let's see a demonstration now from a couple of students.
What we have here is calcite and halite, and what we're going to do today is tell the difference between the two. Halite tastes salty, so we're going to try and see which one it is. This is obviously calcite, doesn't taste salty. This is halite, tastes salty.
The other way we can tell is by putting a drop of acid on them. The halite will not fizz, the calcite will. And this one is fizzing.
Let's take a look at an example mineral here and pretend we're keying it out just like we would if we were in lab. The first thing we need to do is we need to take a look at its luster. And this has a non-metallic luster. So we can go in our lab manual to the flow chart that basically says non-metallic minerals, and it's relatively light in color. The next thing we would do is test its hardness. All right? And in this case, this mineral is going to be pretty darn hard. It's going to be harder than glass. So if you scrape it against the little glass plate that you have in lab, it's going to scratch that glass plate. Next off, we can take a look at its color, which is sort of a peach color here. It is going to be too hard to streak, so it's not going to leave a streak on the streak plate. It's actually harder than the streak plate. And then we would zoom in on its breakage pattern, and in this case, it's got two planes of cleavage. So there's one plane of cleavage on the top of this mineral specimen, and then there's another one on the front. Notice that the top plane is also repeated on the bottom of the mineral specimen, and the front plane is also repeated on the back of the mineral specimen. And on this third surface, like over here, you have an irregular fracture. So two planes of cleavage, we would want to take a look at the angle between those two planes, and in this case that angle is about 90 degrees. So that is going to really help us zoom in on which mineral this is. It's got to be one of the two feldspars. So if we want to distinguish between potassium feldspar and plagioclase feldspar, we want to look for the presence of striations. We don't see any striations here, so it must be potassium feldspar. Another example comes to us from the metallic group of minerals. We note that it has a metallic luster, and then we move on to assessing its hardness. It is softer than glass, so it can't scratch glass, but it's harder than a fingernail. If you drag it across the back of your manicure, you're going to scratch your fingernail, but your fingernail will not be able to scratch it. If you take a look at the streak, it's going to leave behind a gray-black streak, and you will notice that it's got three very well-defined planes of cleavage. So one making up the left and right sides of the specimen, one making up the top and bottom, and one making up the front and back. As you tilt this back and forth in the light, those will be very obvious to the eye. The other thing that you'll notice about this mineral that's very distinctive is it is quite dense. That's because it's lead sulfide, and the presence of lead in the crystal structure makes it a very heavy mineral indeed. All those things add up to mean that this mineral is galena. So it's as simple as that. Basically, start with the classification key on the left side, look at the most basic properties such as its luster, and then zoom in to progressively finer and finer levels of detail to figure out which mineral it is. Once you've figured out which mineral it is, you can assess its economic importance, and you'll have a better sense of where we get our stuff. Thanks a lot for your attention. This has been a pre-lab video.
So I again want to point out that one, you will not be using acid. Please do not taste things. If you think that you may have something that you think should taste salty, you can ask me and I will tell you whether or not it would taste salty. Same thing for acid. I will tell you whether or not it would react. Do not ask me for every single sample you have. I will answer for when you get down to like one or two samples. Remember, if you try to streak something and you do not observe a streak, that means one of two things. One, it's either harder than the streak plate, or it's giving you a streak color that's similar to the plate color. And again, please do not scratch your nail with the mineral. Scratch the mineral with your nail, because so I am next going to show the pre-lab video for the rocks. You will not be looking at samples of the rocks. You will just be doing the parts of the lab that are using pictures, because they're fairly decent pictures. But still, it's important to hear this information.
Hi there, this is Callan Bentley. Welcome back for a pre-lab video. This week in lab, we're going to be taking a look at some rocks. We're going to be thinking about the rock cycle, which is how one kind of rock can turn into another kind of rock. And we're going to identify rocks with the aim of interpreting the conditions under which they formed. This is a diagram in your lab manual describing the rock cycle. You can see that there are sort of 5 major points here on this rock cycle, and there are all kinds of arrows leading from these different hubs towards one another. So first off, let's start with molten rock in the upper left corner. If molten rock is underground, we call it magma. If it's above ground, we call it lava. Regardless, that molten rock can cool and crystallize, and when it cools and crystallizes, it makes igneous rock. So the upper right corner of our diagram shows igneous rock. If igneous rock forms above the surface of the Earth, we call it extrusive igneous rock. And if it forms below the surface of the Earth, we call it intrusive igneous rock. Now, those igneous rocks can be weathered and broken down to produce sediments. So weathering produces sediment. That sediment is then transported away from its origin and ends up somewhere else where it's deposited. And then that sediment gets stuck together through the processes of lithification. It can get compacted or squeezed tighter, or new mineral cements can basically stick the individual grains of sediment together. This makes sedimentary rock. That sedimentary rock might be exposed to excessive heat or pressure, and that can cause it to metamorphose. If you metamorphose sedimentary rock, you end up with metamorphic rock. And of course, if you take that metamorphic rock and you heat it up even more, you can end up melting it, forming magma. All right, so now we've come full circle here on our rock cycle diagram. You'll note that there's also some blue arrows in the middle, and those blue arrows basically can lead us from any of these other rocks to different points on the rock cycle. So for instance, we could go from intrusive igneous rock and melt the rock and make magma again to make more igneous rock, or we could metamorphose that intrusive igneous rock. We could take a metamorphic rock and weather it to produce sediment. We could take a sedimentary rock and weather it to produce sediment. We could take a metamorphic rock and metamorphose it. So those are all valid possibilities as well. To identify igneous rocks, you're basically going to be paying attention to 2 things. One is the composition of the igneous rock, and then the second thing is the texture of the igneous rock. Basically, a combination of the texture and the mineral composition will give you the igneous rock name. For instance, if the rock is mostly dark, that gives us something in this column. All right, it's a mafic composition. And if it's fine-grained, that gives us something in this row. The intersection of that column and that row is one rock and one rock only. That's a basalt. So a basalt is fine-grained and mafic. A granite, on the other hand, would be coarse-grained and felsic in composition. And you can see the other textures such as porphyritic, glassy, vesicular, and pyroclastic. They can have various compositions as well. With sedimentary rocks, basically you're going to take a look at a couple of things right off the bat, and then if those don't work, then you're going to default to some other possibilities. First off, you want to look to see if you can make out particles. If a sedimentary rock is made out of chunks of other rocks, that makes it a detrital sedimentary rock. It can be made out of big chunks, gravel. It can be made out of medium-sized chunks called sand, or it can be made out of very small chunks, which we call silt or clay or mud. If the sedimentary rock fizzes when you put hydrochloric acid on it, that indicates that calcite is one of the major minerals in that rock, and therefore it's going to be some variety of limestone. All right, you can see there's various kinds of limestone depending on the different distinctive properties. So if your rock doesn't fit one of those 2 categories, if it's not detrital or limestone, then it might be one of these other possibilities down here. We could have really fine-grained quartz, which is going to be so fine-grained you can't see the individual grains, but it'll scratch glass, so it's nice and hard, and it may have a conchoidal fracture. Depending on the color, that gets one of several different names. It could be gypsum, in which case you can scratch it with your fingernail. Halite would taste salty, and altered plant fragments make coal. That coal is going to be distinctive because it's black and it's brittle. Okay, with metamorphic rocks, the essential breakdown is going to be foliated or non-foliated. Examples of foliated metamorphic rocks are shown up here on the top. That's where there's an alignment of the mineral grains within it. Marble and quartzite, anthracite coal, hornfells, those are all nice examples of non-foliated metamorphic rocks. Metaconglomerate can be either foliated or non-foliated, and serpentinite is probably best classified as non-foliated as well. Here it's going to be a little bit less systematic. The first thing you should look for is whether there's foliation or not, whether there's an alignment of the mineral grains, but then those distinctive properties are going to be critical for identifying the individual metamorphic rocks. Let's go to my students now and take a look at a couple of examples.
Here we have a primary sedimentary structure, mud cracks. We can tell two things from this. We can tell because of the cracking that it was exposed to the air. If it was underwater, it could not have dried out. And the red color indicates that it was in an oxygen-rich environment.
So here we have two non-foliated metamorphic rocks, marble and quartzite. Now they're both very similar. They both have a sugary texture. The only way we can really tell the difference is with acid. The marble, which is made out of calcite, should fizz. The quartzite, which is made out of quartz, should not.
Here we have a granite rock, which is igneous and it's formed from magma that was underground and it was cooled and uplifted, and it can be weathered away and create sediments like this gravel here.
The sediment can then be transported and lithified later and made into a conglomerate like this, which is a sedimentary rock. And then it can later be under pressure or heat and made into a metamorphic rock like this metaconglomerate.
Okay, so summing up here, you can see three different outcrops here, and these three different outcrops are made out of three different kinds of rock, which tell three different stories. The example up at the top shows a bunch of basalt. That basalt is vesicular, meaning it has gas bubble holes in it, and that tells us a story of ancient lava eruptions. So there was a volcano that erupted there at that site in the distant past. The image in the middle shows a cross-bedded sandstone. And that sandstone, based on those big crossbeds, that must be the signature of an ancient sand dune. Lastly, down at the bottom, we see the kind of rock that we'd find deep at the bottom of the Grand Canyon. That's a schist. And that schist, as I mentioned in the introduction, is indicative of ancient mountain building processes. So when we see a schist, we should imagine the roots of ancient mountain ranges. It's funny to imagine that the Grand Canyon, which is a big hole in the ground, actually used to be at the roots of ancient mountains, but that's indeed what that schist is telling us. Hopefully all this makes sense to you. Thanks a lot for your attention. I hope you have a great time in lab this week identifying these different rocks. This has been another pre-lab video.
So again, this week we're not going to be looking at rocks, we're just going to be looking at minerals. So that is all for this lecture. This one was long, it was a lot of material. Again, please do read your chapter. And that is all for minerals, rocks, and the rock cycle.